280 million years. That is the entire amount of time that had elapsed between the beginning of the universe and the moment light left the galaxy we are about to talk about. That light traveled for the next 13.5 billion years across an expanding void until it landed on a beryllium mirror parked a million miles from Earth in April of 2025. The object is called MOEM-Z14. Its redshift is 1444, the highest ever confirmed for a galaxy. And in January of 2026, the peer-reviewed paper describing it appeared in the Open Journal of Astrophysics under a title that tells you exactly how the researchers felt about what they found. They called it a cosmic miracle. Here is why that word was chosen. MOEM-Z14 is small. It measures roughly 240 light-years across, which makes it about 400 times smaller than the Milky Way. It holds about as much material as the small Magellanic Cloud, the dwarf galaxy that trails our own. When the James Webb Space Telescope caught it, the galaxy was in the middle of a violent burst of star formation, converting gas into stars at a pace that should not have been possible yet. And when astronomers examined its chemistry, they found it was rich in nitrogen relative to carbon, in a ratio that closely resembles the globular clusters orbiting the Milky Way today. Those clusters are the oldest structures we can study up close. Finding the same chemical fingerprint 280 million years after the beginning suggests that stars were already forming in something like their modern way, at a moment when the standard picture says the universe should still have been assembling its first crude generation of them. Rohan Naidu at MIT's Kavli Institute led the work. In a statement released by NASA in January of 2026, he said that with Webb we can now see farther than humans ever have, and that what is out there looks nothing like what we predicted. That is the sentence to hold on to. Not that the predictions were slightly off, that they look nothing alike. Now, a necessary clarification, because the internet will tell you otherwise, and the internet is wrong. None of this breaks the Big Bang. The universe is still 13.8 billion years old. The cosmic microwave background is still there, still glowing at the temperature the theory predicts. Big Bang nucleosynthesis still accounts for the hydrogen and helium ratios we measure. Expansion is still expansion. Every load-bearing pillar of the model is standing exactly where it was. What is falling apart is everything that comes after. The models describing how quickly clouds of primordial gas collapse into stars, how quickly those stars manufacture heavy elements and blow them back out, how quickly black holes grow from nothing into millions of times the mass of the sun. That timeline is in genuine trouble. The universe apparently built structure far faster than any simulation said it could, and the further Webb looks, the worse the problem gets. To understand why the numbers matter, you need to understand how astronomers measure them. As the universe expands, it stretches the wavelength of light traveling through it. Light emitted as ultraviolet arrives as infrared. The longer the journey, the greater the stretch. That stretch is redshift, written as Z, and it is the closest thing cosmology has to a reliable odometer. Redshift 14 puts you inside the first 300 million. There's a specific feature astronomers hunt for. Neutral hydrogen in intergalactic space absorbs everything below a certain wavelength and lets longer wavelengths pass. The result is a hard cliff in a galaxy's spectrum, a point where the light simply stops. That cliff is called the Lyman break, and its position tells you the redshift. Photometrically, you can spot the break by noticing that a galaxy is invisible in one filter and suddenly bright in the next one over. That is fast, and it is how candidates are found. But it is also where the mistakes live, and we will come back to that, because one of the most extraordinary claims of the last 2 years died on exactly that point. Consider how quickly the record has moved. Before Webb launched, the most distant galaxy anyone had confirmed sat at a redshift of about 10 or 11. Hubble found GNZ11 at redshift 11, seen 430 million years after the beginning, and even that object was described as having extreme properties as an outlier that nobody quite knew what to do with. Astronomers expected Webb to push the frontier outward gradually, one careful step at a time, over the course of a decade. Webb switched on fully in July of 2022. By December of that year, JWST Z13.0 had been confirmed at redshift 1320, roughly 400 million years after the beginning. That was not a step. That was a leap past everything Hubble had managed in 3 decades, achieved within months of first light. In May of 2024, the record moved again. A team working on the JDES survey, the JWST Advanced Deep Extragalactic Survey, announced 2 galaxies found in a patch of sky near the Hubble Ultra Deep Field in the constellation Fornax. They called them JD's GS-Z14-0 and JD's GS-Z14-1. The first of the pair sat at redshift 1418, seen roughly 290 million years after the beginning, and it held the title of most distant confirmed galaxy until MOEM-Z14 took it. But the reason JD's GS-Z14-0 matters more than its record is what happened next. because that galaxy is not the story. What astronomers found inside it is the story. Start with its size. JWST Z1420 is more than 1,600 light years across, and it is bright, uncomfortably bright. At that epoch, the expectation was that any galaxy you managed to detect would be a faint smear, barely coherent knot of gas beginning to organize itself. Instead, here was an object large enough and luminous enough that its light crossed 13.4 billion years and still registered clearly. Something had already assembled it. Then, in March of 2025, two independent teams pointed the Atacama Large Millimeter Array in Chile at the same galaxy. ALMA does not see the same light Webb sees. It works at millimeter and submillimeter wavelengths, which lets it detect emission from specific elements. One team was led by Stefano Carniani at the Scuola Normale Superiore in Pisa, publishing in Astronomy and Astrophysics. The other was led by Sander Schoes at Leiden Observatory in the Netherlands, publishing in the Astrophysical Journal. They worked separately, they analyzed the data independently, and they found the same thing. You need to sit with what that means, because it is the single most damaging observation in this entire subject, and it is more damaging than any record for distance. Oxygen did not come out of the Big Bang. The early universe produced hydrogen, helium, and a trace of lithium. That is the whole inventory. Everything else on the periodic table, every atom of carbon in your body, every atom of iron in your blood, every atom of oxygen in the air you are breathing right now, was manufactured inside stars by nuclear fusion and then scattered across space when those stars died. That is the only mechanism there is. There is no other factory. So finding oxygen in a galaxy at 290 million years means a full generation of massive stars had already condensed out of primordial gas, burned through their fuel, fused hydrogen into helium and helium into carbon and carbon into oxygen, and then exploded as supernovae to distribute the results into the surrounding medium. All of it, completed, inside a window shorter than the time separating us from the dinosaurs. And it was not a trace. Both teams found that JWST Z14-0 contains roughly 10 times more heavy elements than the models predicted for that epoch. 10 times. Not a modest excess that could be waved away as measurement noise, but an order of magnitude of chemistry that theory says should not have existed yet. Sander Schoes described the result with a line that has been repeated in every article written about it since, and deservedly so. He said it was like finding an adolescent where you would only expect babies. Carniani, on the other side of the collaboration, said he was astonished by the results because they opened a new view of the first phases of galaxy evolution. Gergo Popping, an ESO astronomer who had no involvement in either study, said the clear detection surprised him and that it suggests galaxies can form more rapidly after the Big Bang than previously believed. The follow-up work went deeper still. Astronomers pointed Webb's mid-infrared instrument at JWST Z14-0 using its low-resolution spectrometer, scheduling roughly 51 hours of observation. One set of those observations failed, leaving about 34 usable hours, which, even after the loss, remains by a wide margin the longest spectroscopic integration ever attempted with that instrument on any target. What came back was a rest frame optical spectrum of a galaxy at redshift 1418. The analysis found that the galaxy is a prolific producer of ionizing photons, and that a significant fraction of those photons appear to be escaping into the intergalactic medium, carving out one of the earliest bubbles of ionized gas anywhere in the cosmic record. And it confirmed the high metal content, with the authors stating plainly that existing simulations struggle to reproduce chemical enrichment happening that fast. That phrasing is worth noticing. Not that the simulations are wrong, that they struggle. This is what a field looks like when the data has outrun the theory and everyone knows it. And JWST Z14-0 is not an isolated freak. In March of 2026, astronomers announced EGS Z11R0, the most distant red galaxy ever detected, at a redshift of about 11.45. That designation matters more than it sounds. Galaxies at these redshifts are supposed to be blue because they are made of very young, very massive stars pumping out ultraviolet light with almost no dust to absorb it. Dust is a late arrival. Dust is manufactured by dying stars the same way heavy elements are. A red, dust-rich galaxy at redshift 1145 is another object insisting that generations of stars had already come and gone. Then there's the case that reverses the problem entirely. In 2023, a team led by Tobias Lusser reported a galaxy that had already stopped forming stars when the universe was around 700 million years old. Not forming slowly, quiescent, dead. A galaxy that had run through its available gas, built its stars, and gone quiet, all before the universe finished its first billion years. So the pattern is not one weird object. It is a systematic direction of error. Everywhere Webb looks in the early universe, things are bigger, brighter, more chemically developed, and further through their life cycle than the models allow. This brings us to the argument that genuinely rattled cosmology, and to the part of the story where it is important to be honest about how it turned out. In 2022 and 2023, working with some of the first public Webb data, a team led by Ivo Labe identified 6 galaxies at redshifts between 7 and 10 with colors so red that the implied stellar masses came out above 10 billion times the mass of the Sun. These were objects seen roughly 500 to 700 million years after the beginning, carrying as much stellar material as a substantial modern galaxy. Michael Boylan-Kolchin then wrote the analysis that turned an anomaly into a crisis. In the standard cosmological model, galaxies form inside halos of dark matter. The halo collapses first, ordinary matter falls into it, and stars form from that ordinary matter. The model makes a firm prediction about how many halos of a given mass exist at a given time. Boylan-Kolchin's point was devastating in its simplicity. At those redshifts, there are not enough sufficiently massive halos to contain galaxies that heavy. Not merely unlikely, not present in the required numbers, even if you assume every single baryon inside every halo were converted into stars with perfect 100% efficiency. Real galaxies do not manage anything close to that. Star formation is wasteful. Observed efficiencies run at a few percent. A model that requires 100% is not a model that needs adjusting. It is a model that has been contradicted. The response was immediate and frankly chaotic. Papers appeared proposing warm dark matter, which would change how structure grows on small scales. Papers proposing fuzzy dark matter, cosmic strings, or primordial black holes acting as seeds to accelerate collapse. Papers proposing primordial non-Gaussianity in the initial density fluctuations, meaning the seeds of structure were distributed differently than we assumed. Papers proposing a gradual shift in the stellar initial mass function, meaning the early universe made systematically heavier stars than it does now, which would change how much light you get per unit of mass. One of the more elegant proposals connected the problem to a completely separate crisis. Early dark energy was originally invented to address the Hubble tension, the persistent disagreement between two different methods of measuring the expansion rate of the universe. Researchers found that an early dark energy model also brings the ultraviolet luminosity functions of high redshift galaxies into line with observation. One exotic ingredient, 2 unsolved problems. That is the kind of coincidence that makes theorists pay attention. And then, over the following 3 years, a great deal of that crisis quietly deflated. This is the part most videos on this subject leave out. And leaving it out is how you end up narrating a story that stopped being true in 2024. The first problem was that the original mass estimates came from photometry. You measure brightness in a handful of filters and fit a model of what kind of stellar population would produce those colors. It works, but it is vulnerable. Extremely strong emission lines from ionized gas can dominate a broadband filter and make a galaxy look far more massive than it is. Some of the original candidates turned out to be something else entirely. Spectroscopic follow-up of one of them revealed not a massive galaxy at all, but a low luminosity quasar at redshift 5.6, hosting a black hole roughly the mass of the Milky Way's own. The second correction came from the mid-infrared. A survey called PRIMER, covering the cosmos and UDS fields with both near-infrared and mid-infrared imaging, sampled a volume 5 times larger than the one used in the original analysis. Mid-infrared data constrains stellar mass far better, because it sees the older, cooler stars that actually carry most of a galaxy's weight. The census that came back showed the true number density of massive early galaxies was substantially lower than the first estimates. A separate survey called FRESCO examined 36 massive galaxies between redshifts 5 and 9 and found no fatal tension with the standard model at all. In 2026, the theoretical side closed the loop. A team using the UCRO-U simulation, a calculation following 2.1 trillion particles, argued that the stellar mass-to-light ratios required by the original claim were not physically achievable in the early universe, and that standard cosmology reproduces the observed ultraviolet luminosities without any new physics. And in April of 2026, Jay Krishnan and Kevork Abazajian at the University of California, Irvine, published a paper whose title states the outcome directly. They called it a resolution of the massive early galaxy tension. Their framework accounts for multiple sources of uncertainty simultaneously, and when you do that properly, the required efficiencies fall back into the range that ordinary galaxy formation can supply. So the mass crisis has largely been resolved. If someone tells you Webb proved the standard model wrong by finding galaxies too heavy to exist, they are describing an argument that was strong in 2023 and has been substantially answered since. But notice carefully what has not been resolved. The mass problem shrank because the masses were overestimated. The chemistry problem did not shrink because oxygen is oxygen. You cannot revise away an emission line at a known rest wavelength. JDIS GS-Z140 still has 10 times more heavy elements than it should at 290 million years, measured two ways by two teams, and confirmed by the deepest mid-infrared spectrum ever taken. The speed problem is real, and it is still standing, which brings us to the object that would have destroyed everything if it had been what it appeared to be. In September of 2025, a team led by Giovanni Gandolfi reported a source in the Sears survey, catalogued as U-10588, which they nicknamed Capotauro. It sits in the constellation Botas. Its properties were, on paper, absurd. It has a magnitude of about 2768 in Webb's F44W filter, and below 3.5 microns it is not there at all. Between 3.5 and 4.5 microns, the flux drops by more than 3 magnitudes. That is a cliff far sharper than anything seen in an ordinary galaxy. Interpreted as a Lyman break, that cliff implies a photometric redshift of approximately 32. Take a moment with that number. Redshift 32 corresponds to roughly 90 million years after the Big Bang. That is nearly 200 million years before MOEM Z14. It would place this object in the era of the very first stars, before the first supernovae, before there was any mechanism to enrich anything, and the implied ultraviolet luminosity was around minus 21.5, meaning it would have to be bright, which at that epoch means it would have to be substantial. The team was careful. They combined Webb's NIR-CAM imaging, MIRI photometry, and NIR-SPEC spectroscopy with archival Hubble data. They ran multiple independent spectral fitting codes. They deliberately tested alternatives, including dusty galaxies at redshift below 10, strong emission line objects, Balmer break sources, and the possibility that it was a substellar object inside our own galaxy. Every extragalactic configuration they tried kept converging on the same answer. Only about 0.5% of the redshift probability sat below redshift 25. The paper appeared in Astronomy and Astrophysics in February of 2026. Gandolfi said it could be the farthest galaxy ever seen, at a timescale compatible with the formation of the first stars and black holes in the universe. Others were not convinced, and their skepticism was pointed. Nisha Lee Thochwalit put the stakes plainly. If it really is a galaxy at redshift 32, then a great many of the things we currently believe would have to be wrong. There was an alternative on the table from the beginning, and it was not exotic at all. A brown dwarf is a failed star, an object too small to sustain hydrogen fusion, glowing faintly from the heat of its own formation and slowly cooling forever. The coldest ones, classified as Y dwarfs, have atmospheres full of methane and water vapor that absorb light in specific bands. The result is a spectral energy distribution with a sharp drop between 3 and 4 microns, produced by molecular absorption rather than intergalactic hydrogen. From Webb's perspective, a Y dwarf a few hundred parsecs away in our own galaxy and a Lyman break galaxy at the edge of time can look remarkably similar. This is not a new failure mode. Brown dwarfs were mistaken for high redshift galaxies in Hubble surveys decades ago, and a JDS survey paper published in 2025 cataloged an entire population of cold T and Y dwarfs lurking in deep extragalactic fields, contaminating exactly the searches that are supposed to find the earliest galaxies. There was one way to settle it, and it required patience rather than cleverness. Everything inside the Milky Way moves. Stars orbit the galactic center, and over time their positions against the background sky shift measurably. That apparent motion is called proper motion. A galaxy at cosmological distance has none. It cannot. There is no amount of velocity that produces measurable angular displacement across billions of light years on a human timescale. So if the object moves, it is local. If it does not move, it is not. The discovery data was 3.5 years old. In August of 2026, a team obtained new medium-band NIR-CAM imaging of the same field and compared the two epochs. They used filter-dependent point spread function fitting, built a local astrometric reference frame from 68 compact background sources, and ran a joint injection and recovery analysis across 4 images to make sure they were not fooling themselves. Capotaro had moved 132 milliarc seconds, plus or minus 20. A milliarc second is 1/3,600th of a degree, divided by 1,000. This is a shift you would never see by eye in a lifetime. But it is enormous compared to the measurement precision, and it rules out any extragalactic interpretation at better than 6 sigma. Not a galaxy, not an active galactic nucleus, not a supernova, nothing outside our own galaxy. Comparing its spectral energy distribution against empirical templates, the best fit is a brown dwarf of spectral type Y1, give or take half a subclass, with an effective temperature of approximately 350 Kelvin, that is around 77 degrees Celsius, cooler than boiling water. The distance came out at 730 parsecs, plus or minus 110, which places it comfortably within the scale height of the Milky Way's stellar disk. The most distant object ever claimed turned out to be a lukewarm failed star in our own neighborhood. It would be easy to tell that as a story about hubris. It is not. It is a story about how the field is supposed to work, and it is the reason you should take the surviving results seriously. Kapataro was proposed openly, tested aggressively, and killed by a measurement that the people who proposed it knew was coming. Meanwhile, MOMZ14 and JWST have been subjected to spectroscopy, to independent analysis by competing teams, to the deepest integrations their instruments can deliver, and they have not moved. The anomalies that remain because nobody has been able to kill them. And there is one more that is refusing to die, which brings us to what is arguably the strangest thing Webb has found. They are called little red dots. They started showing up at the end of 2022 in enormous numbers in Webb's deep field images, compact, intensely bright, distinctly crimson. They appear roughly 600 million years after the Big Bang. They persist for a while, and then they vanish from the record almost entirely by the time the universe is 2 billion years old. Jorrit Matthey, who coined the name, initially described them as baby quasars. They have three properties that, taken together, defeated every explanation offered for 3 years. Their spectra are V-shaped, dropping and then rising in a pattern that does not match ordinary stellar populations. They are extraordinarily compact, far more concentrated than a galaxy of the implied brightness should be. And spectroscopy has revealed nitrogen-enriched chemistry that neither star-forming galaxies nor standard black hole accretion naturally produces. When Matthey and colleagues published their landmark analysis in 2024, the numbers implied a population of supermassive black holes in the early universe far larger and far more numerous than any formation model permits. That is where the phrase about Webb-breaking cosmology came from. Making it worse, supermassive black holes should announce themselves in X-rays and radio, and for a long time, neither had been detected from these objects. The unraveling began in January of 2026 with a study published in Nature led by Vadim Rusakov. His team analyzed 12 of these objects, the earliest of them seen when the universe was around 840 million years old, and found that the black holes inside little red dots are likely about 100 times less massive than the earlier estimates suggested. The reason was subtle and instructive. The black holes sit inside dense cocoons of hot ionized gas, and that gas was broadening the spectral lines in a way that mimicked the signature of a far heavier object. The measurement had been reading the cocoon, not the engine. That is a factor of 100. Most of the cosmological emergency evaporated with it. In April of 2026, an X-ray signal was finally detected coinciding with the position of a little red dot, which strengthened the leading model considerably. Then, in June, a team led by Vasily Kokorev at the University of Texas at Austin published the deepest spectrum ever obtained of a single one of these objects. The target was Glimpse 179/5, sitting behind the galaxy cluster Abell S-Tome 63, magnified by the cluster's gravity. Webb spent 30 hours on it, and gravitational lensing made that equivalent to roughly 80. The spectrum contains more than 40 independent emission lines, including signatures indicating electron scattering, which is what you expect when a radiation source is buried inside an enormous shroud of gas. Kokorev said that part of the community is converging on a single picture, that little red dots can be explained by black hole star models, but that no previous example had all the pieces of evidence in the same place. A black hole star is a strange object to imagine. It is a rapidly growing supermassive black hole wrapped inside a cocoon of hot, partially ionized gas so thick and so extended that from the outside, the whole system behaves like an enormous star. The black hole feeds from the inside. The cocoon glows from the energy released. And the reason little red dots disappear from the cosmic record is that this phase ends. Either the growth spurt burns itself out, or the black hole eventually clears the surrounding material and emerges as a recognizable quasar. Then, in the second week of August 2026, two things happened within days of each other, and they do not agree. On the 5th of August, researchers at the Harvard Center for Astrophysics published a pair of studies proposing something else entirely. In their model, little red dots are not black holes wrapped in gas. They are stars. Specifically, supermassive stars of roughly 100,000 solar masses, pulsating violently and shedding shells of gas in the final stages before they collapse to form the first supermassive black holes. Their claim is that this is the first model capable of explaining all three defining oddities simultaneously: the V-shaped spectra, the compactness, and the nitrogen chemistry. And then, roughly a week later, a paper in Nature reported the discovery of MOMB-H1, the earliest black hole star yet identified, observed as it was 660 million years after the Big Bang. It emerged from the same mirage or miracle survey that produced MOMZ14, a program Matthey described as having been designed specifically to target risky sources, objects that could turn out to be either extraordinary discoveries or interlopers like cold nearby stars masquerading as distant galaxies. MOMBH1 is the best example yet of what researchers call a naked black hole star. Naked, meaning it appears to exist on its own, not embedded inside a host galaxy. There is a much brighter galaxy nearby, and models suggest the two will merge in roughly 100 million years. When the team combined the spectra of the two objects, the result closely reproduced the characteristic appearance of a little red dot, which offers a concrete physical template that can now be tested against everything else in the catalog. Sit with the implication of a naked black hole star. The standard sequence is that gas collapses, a galaxy forms, and somewhere in the dense center of that galaxy, a black hole grows. Here is an object suggesting the black hole came first, and the galaxy is arriving later as a separate body that will eventually fall in. That inverts the order of assembly. So where does this leave us? The Big Bang is intact. The age of the universe has not changed. What has changed is the schedule. Galaxies were assembling, enriching themselves with heavy elements, and in some cases finishing their star formation entirely within the first few 100 million years, faster than simulations can reproduce. Black holes were reaching enormous masses at epochs that leave very little time to get there, and at least one of them appears to have done so without a galaxy around it. The mass crisis of 2023 has largely been answered. The speed crisis has not. What comes next will not wait long. The Nancy Grace Roman Space Telescope, an infrared observatory built to survey vast areas of sky rather than stare at small patches, could launch as soon as late 2026, and it is expected to produce high redshift candidates in industrial quantities. Most of those candidates will be wrong. Some fraction will be brown dwarfs, exactly like Capitaro, and separating them will take years of the same patient, unglamorous verification work that killed the redshift 32 claim. But Webb may break its own record again before Roman even reaches orbit. The authors of the MOEM Z14 paper wrote that the telescope appears poised to drive a series of great expansions of the cosmic frontier, and that redshifts once considered unimaginable, approaching the era of the very first stars, no longer seem far away. That is the honest ending. Nobody has overturned the Big Bang. What they have overturned is our confidence that we knew what happened next. 280 million years in, something was already burning out there, already making oxygen, already too developed for its age, and every time the telescope looks further, it finds that the universe got started earlier than we gave it credit for.